And in today's webinar, we have a presentation about two interface options of the AnyBody modeling system that were developed as part of the Digital Exonomics Research project. My name is Christopher Iversen, and I work here at AnyBody Technology. And today I'll be the host of this webinar, and I'll be assisted by my colleague Bjørn Ingelund at the Q&A session in the end. And in the AnyBody webcast series, we host presenters who have worked with the AnyBody modeling system to cover different use cases. And in today's webcast, I would like to introduce two speakers. First of all, I would like to say that originally we have Anna Jensen as one of the speakers, but unfortunately she became ill. So Dr. Sascha Ullmann is taking over for her part. And Sascha Ullmann is the head of digital planning and ergonomics at IMK Industrial Intelligence. And in the second part of this webcast, we have Lukas Grossman, who is a biomechanics research associate at the Laboratory for Biomechanics at OTH Regensburg. And Sascha and Lukas will give us insights on these two new interface options that were developed in the Digital Exonomics project. And to begin with, Sascha will do a presentation on the interface between AnyBody and the ergonomic human model EMA, which is embedded in the software system EMA Work Designer. And here you can facilitate biomechanical analysis options in the context of ergonomic work design in industrial settings. And after this, Lukas will show how motion data collected with the Captury's Markerless tracking system can be used in the AnyBody modeling system, and how the result of this Markerless tracking system compare to marker-based motion analysis. And the presentation will start in a few minutes or so. But just before we start, I will just give you a very short introduction to the AnyBody modeling system, if there's any of you who are unfamiliar with the software or musculoskeletal modeling and simulations in general. So first of all, I would like to draw your attention to the control panel, which appears on the right side of your screen. And here you are very welcome to submit questions and comments via this question panel during the presentation. And I'll try to address these questions at the very end of the webinar. And in case we do not get to answer all of your questions, we'll try to do so by email within a reasonable time. But let's begin with having a look at what the AnyBody modeling system actually is. So the AnyBody modeling system is a software that allows you to do musculoskeletal modeling and simulations. And as input, it takes motion data as kinematics and forces, and it calculates the internal body loads as joint reaction forces, muscle activity, and metabolic energy. And at the moment, AnyBody is used in a wide variety of areas and applications. And just to give you a few examples of this, then it could be movement analysis, product optimization design, the field of sport optimization, orthopedics and rehabilitation, ergonomics that could be with and without assistive devices, as for example an exoskeleton, and also in the automotive industry. And a typical workflow in AnyBody could look something like this. So basically you provide the recorded motion data as input, and then you can use the body models which comes with the AnyBody managed model repository, which have been built by many users around the world. And then you can provide some kind of environment, which could be a special type of equipment, for example, an exoskeleton, as it is in this case. And then you can use AnyBody to combine these things and solve the muscle recruitment and run the inverse dynamics simulation. This basically means that we go from motion to calculating the internal body loads and the interaction with the environment in some cases. And then you can output the result and use it for some kind of post-processing, which could be with a finite element tool. But there's also many users who choose to complete this loop by doing some kind of design optimization and then run this cycle multiple times. And this actually brings me to the end of the introduction. So I'll hand over the presenter role to Sascha instead.
And yes, because I hasn't mentioned it, normally it should be Anna here, Miss Anna Jensen, my colleague for my team, but yeah, unfortunately she is got sick in, and now I do the presentation. I'm the head of digital planning and ergonomics at IMK, and in the next couple of minutes I want to present you our research project Digital Exonomics and our interface EMA to AnyBody and what you can do. First link between the worlds of biomechanical digital human modeling and 3D production planning with our EMA Work Designer. First of all, maybe some short introduction in the Digital Exonomics Research project with the topic of the digital work design and ergonomics assessment for the use of occupational exoskeletons. It was a research project by the Federal Ministry for Education and Research in Germany, with project partners like Captury for motion capturing, the Fraunhofer IPA, the Technical University of Regensburg, and the IMK Industrial Competent, the company I'm working on. And also some associated partners, especially for the practical part of the research project, for examples and studies like Daimler Truck, Deutsche Bahn, DB Schenker, Otto Bock, and of course AnyBody, and some more medical partners in the medical sector. The research project was the start in the February of 2021 until the February of 2024, and this year. And today I want to show some results connected with this research project, but also with research projects before, like we had a research project EMA to AnyBody some several years ago. And yeah, what was our focus of this research project? It was the goal for an early efficiency analysis of exoskeletons using validated 3D simulations and markerless motion capture systems, especially here with Captury. And this means our goal and our work task in the research project was to create and enhance the interfaces between several systems. First of all, for markerless motion capturing with the software system Captury, the biomechanical human model of AnyBody, like Christopher mentioned it before in the last minutes. I think it's also very important now to understand also how these software systems can be connected, and also, of course, our ergonomic human model EMA, ended in the EMA Work Designer, for the goal of detailed analysis and evaluations when it comes to ergonomic assessment of motions, of work tasks, of workplaces. It means also we can wider the view on the designing of work processes, especially also with exoskeletons, without exoskeletons, with exoskeletons, and so on. And this means also one of the subjects here on the focus was several interfaces we want to show to you today. It means the interface between Captury and AnyBody is the second part of the webcast, and the first part from my side, the interface between AnyBody and EMA. But maybe first of all, I want to give you a brief introduction about our company, what is IMK and what is EMA and the EMA Work Designer. And first of all, our company IMK Industrial Intelligence was founded more than 20 years ago, 2002. We are located in Germany, in Saxony, and Chemnitz is our headquarter, with approximately a little bit more about 50 employees. And we was in the past a conventional consulting company, engineering company for production planning, optimization, lean management, etc. But the last 15 years, we developed our own software system called EMA, EMA Human Model, ended in a software suite called EMA Software Suite. And I think it's quite unique because we are not only doing software distributions, we are also company with an own software development team located in Chemnitz here in Germany for our software system, and of course based also on our past, we're doing industrial projects, research projects with our own software system for our consultation services. Yeah, with more than 500 clients, 2,000 projects, and we are worldwide active, especially Europe and Asia, and also in US, America. But what's all about the EMA software suite? Very short here, the EMA software suite contains two tools, but we will focus today on the EMA Work Designer. But only here to complete everything in our EMA software suite, we have a so-called EMA Plant Designer on the macro level for factory planning, for space requirements, resources, material flow simulation, value stream mapping, and so on. But also when it comes to the workplace design, production lines, production areas, machinery, equipment, we use our EMA work designer on the micro level, on workplace level, with layouting, simulation, production times, ergonomics, and so on. And both are connected in the EMA software suite. That means our users can, first of all, plan a factory and then go into the details of designing work processes and workplaces. And also we have some more functionalities like virtual reality in our software system, the topics of human-robot collaboration, robot simulation together with humans, especially also for the risk assessment in such a case of collaboration. And also more interfaces like with EMA to AnyBody or with HaloGlide VR or also with NVIDIA Omniverse. I think in the last month, years, this is a very growing topic to connect many different software tools in one master system like Omniverse. Here we have also a connector which enables a very easy data exchange, high-end rendering, and real-time collaboration. But today we want to focus on EMA Work Designer and how we can connect it to AnyBody. And here only a very short video to see what's the pearl of the EMA. It's a digital human model. A mannequin, you see, it moves around. It can fulfill work tasks, screwing, clipping, mounting, assembly. We have robots, we have HEVs in the simulation. We can integrate, consider layouts, wax, material, containers, everything what you need for the process planning. It means our software system is, or the main user of our software systems are industrial engineers, production planners, ergonomists, human factors engineers, and so on. To do all the work tasks, what in the past would be conventional way with Excel, Word documents, simple IT tools, you can do now in 3D, the whole process planning. This means also you can do the workplace design 2D, 3D, human, robots. We have a time analysis tool that you can see validated, certified time analysis. How long does a work task need or needs to fulfill by the worker with MTUS, MTV, MTM, HWD. And also productivity analysis like added value and working paths. And of course, if we can simulate human movements, we can also check ergonomics. And we have several industrial standards like EAWS or NIOSH lifting equation integrated in EMA. These are methods for their endurability checks and also some functionalities for job rotations and job profiles. And of course, if you have a video, you can do introductions, documentations, work instructions, and so on. And also connectivity, virtual reality, as shown in the last slide. And also a big part is motion capturing. And this is also one of these interfaces we can use for different systems, like also Captury and the Digital Exonomics Research project, but also these interfaces for different other systems which use GmbH data files like AnyBody. And yeah, I think also it's not only focused on one digital model. You can simulate everything in different shape or scale on factory level, logistics, pre-assembly, cell workshop production, specific applications, body shop, paint shop, also line productions. Not only as simulation, but also in the planning, that you can use the software system to optimize your production planning processes or your production processes when it comes to time, and especially also for the ergonomic part. In the pre-planning phase, that you don't need to go on a cardboard workshop or you need to prototype something in a factory hall. You can do it everything virtually with a digital human model. And yeah, our EMA Work Designer. One last PowerPoint slide here for EMA Work Designer, and then I switch, of course, to EMA to AnyBody. Here are our customers and partners. an excerpt of our customers here, like the automobile industry, OEMs here in Germany, like Volkswagen, Audi, BMW, but also in China, like Brilliance. We have also tier 1 supplier here, Drexelmeier, Kramer, Vision Automotive, Austria, and so on, but also different our industrial sectors. That means the focus on EMA Work Designer is everything you can do in a production. That means also we have some customers in the aerospace like EFW, Flugzeugwerke, or water pumps, Grundfos, or agricultural components, equipment like Horsch, or medical devices like Ottobock. And also, we use our software system for ourselves, for our consulting projects, and also this to our customers like EDAC, engineering services here, or FFT, Dinova, BM Engineering. And we have also several partners here like ETEM, Workplace Equipment, EKS Intec, Virtual Commissioning, NVIDIA, Omniverse, Halo Client, VR, MTM, DMC, ORTIM for time analysis, and of course AnyBody, especially when it comes to enhance such simulations with biomechanical simulation. And maybe to understand how actually motion generation in EMA Work Designer works, we have a motion generator in EMA Work Designer, and this means it's based on a process description. Maybe you want to have a work task, like here as an example, remove reinforcement plates 2 and 4 from container and insert into a fixture V08. And in EMA, we will create tasks. It's not a programming language or script-based language. You have some drag and drop so-called work tasks to give the human digital human model a work instruction. And this is for us a pick task here. Pick a plate from a container and maybe a walk to the object can also be automatically generated, and place an object. And it's not based on motion capturing. It can be based on motion capturing, but here it's based on algorithms we had and development since 15 years. We are working also continuously on these algorithms to create very fast a motion. It means here in this little video you see the first motion sequence based only on 2 inputs I need to do in the digital human model. Pick an object, which object, and automatically the EMA will find its way. We have a collision avoidance, collision detection here with obstacles, and we'll check the environment, move to the container, walk to the container, pick up these objects. And the next one, place an object. That means we need a target, a definition of a target, and then automatically EMA walks to this target and places this objects in a fixture. And this is the normal way we do simulation, human movements in EMA Work Designer. But we have different other options. And one of the parts in the Digital Exonomics Research project and in the research projects before was to combine in an interface between AnyBody's biomechanical human model and EMA both advantages of biomechanical simulation and a 3D process planning with EMA Work Designer. It means a data transfer between EMA Work Designer, our EMA digital human model is entered into EMA Work Designer, enables fast biomedical analysis with EMA movement sequences for industrial use cases. Also, in EMA, we don't use biomechanical analysis. We have a lack of these analysis functions because we have focused on methods for endurability checks like EAWS or Nash lifting equation. And this means also we can now enrich these ergonomic analyses. That is our goal in the EMA to AnyBody interface with biomechanical parameters for detailed and further analysis in the planning process of work tasks, workplaces, and so on. And this means, first of all, a general workflow, how we have in mind how you can use both systems together. And then I come to the concrete interface, and also I will show you a little live demo here. Means, first of all, we have the goal. The production planners, the industrial engineers, the human factors engineer have the goal, okay, I want to check and work process if it's ergonomic. The or I need a redesign for designing an ergonomic work process. And this means, first of all, I need to select a work process for the ergonomic evaluation, a work task. Then here in EMA Work Designer, I start in EMA Work Designer with a 3D simulation of the work process. And then I go into the biomechanical simulation of AnyBody. And I think a very unique thing here is that we now use the movements we generate in EMA Work Designer as an input in the biomechanical simulation with AnyBody. But not only the movement we generate in EMA, it means you don't need an AnyBody to program or script some movements or import motion capture data. You use the motion data from EMA Work Designer, and additionally from our software system comes more informations, metadata, like the weight and shape of objects. And this means also internally it will calculate the external forces as constraints or the reaction forces in the biomechanical simulation. And then you have a very first result that you have improved movements in EMA Work Designer. You can re-import it in EMA. Don't worry, I will show you some examples in the next couple of minutes that you have based on the biomechanical simulation, because our motion generator has algorithms based on different other conditions we use to generate motions. That means also you get a more detailed so-called better movement in EMA Work Designer. And then you are able now to do a wider view on the ergonomic evaluation, because then you have results from the biomechanical simulation via AnyBody. You have muscle joint forces minus Dortmunder doses model for the trunk L5S1, but also ergonomic methods here integrated in EMA Work Designer with EAWS or the NIOSH system. And this means you have a wider view and or forward analyzes functionalities for your ergonomic evaluation. And then as a user of the both software systems, as a production planner, I can now say, okay, if this ergonomic work process based on these new KPIs, ergonomic or not. If yes, then I can release the work process and can continue the production planning. If not, then I can also go into EMA again, optimize the process, the product, the workplace design for an approved motion sequence, and then the workflow starts again to check after the simulations, okay, what are my new results? Is this new ergonomic work process? And this was the general workflow we had in mind to develop such an interface between both software systems. And maybe how it looks, first of all, because afterwards I come to the very detailed functionalities. That means we have an EMA simulation. Here, a very easy example, load handling, pick up a container with 5 kilograms. It's an EMA simulation, automatically generated. Then it comes to the data transfer in AnyBody. This means our digital human model needs to be transferred in AnyBody. It means the movement data is based on a vector model we had also here created in the research project. And then we can do the AnyBody simulations, here transferring the movement data we had from our digital human model in the digital human model from AnyBody in the musculoskeletal system here. And afterwards, after the simulation, we create a new simulation in EMA Work Designer with the optimized movement based on every constraint we can here consider in AnyBody with the biomechanical or biomechanical simulation. And it's not only a visualization. Okay, maybe this movement looks realistic or a little bit more realistic than this movement automatically generated in EMA, but you get also all the results. Here a short example. Here in comparison, both movements. Here also in 3D environment, we had not only an empty room, you can also create now layouts and workplaces in EMA Work Designer, and we import the movement informations. It means also here you see the the human model and the transparency style, it's the movement from EMA, automatically generated. And here one of the goals or one of the results from the research project, here the full color digital human model is the optimized motion from AnyBody in our software system using the new interface. And this means also I can now enhance my results when it comes to workplace design, to process designing. It means I have an AnyBody, for example, new results I can use in EMA with muscle activities or also joint angles and so on, forces. But also you can now combine it with EMA results, with time analysis, how long does it work tasks take, but also the ergonomics in EMA, and for example here the EAWS or also joint angles, we are doing it also in EMA Work Designer, but based here on limits referred to German standards, yellow, green, and red here, for example, for the upper body stooping. It means also I can do now with this interface and to get a better look on different ergonomic assessment methods right now to complete, to do a complete ergonomic analysis, also considering biomechanical analysis and functionalities from AnyBody. And maybe one short PowerPoint slide, how does the interface now works? And that means in the research project we created also some tools with the aim that we have a very user-friendly connection between both systems with not much more clicks. A user want to do fast and quick the ergonomic assessment. And here you see the workflow. That means here the blue colored block is an area in which the user operates. They need manual things to do. And here the light blue version block, it's automatically in the background. And it means, like in the general workflow, first of all, we create the EMA scenario, and then we can create with the EMA scenario, with the movement of the digital human model and BVH file. It's a motion file we can use in AnyBody. And then here we use two batch files. One batch file is an ANY MCR batch from AnyBody. It was already integrated in AnyBody. And new here developed in the research project a Windows batch file. And this adjustment means here I only need to input some file paths and to start the Windows batch. It's a batch file, and this means after starting the batch, it will automatically start the AnyBody batch, starts AnyBody in the background and do the simulation in AnyBody. Without programming something in AnyBody, it's automatically based on the human motion of EMA Work Designer. And then you get all the AnyBody output as text files, as movement data. The regularly export is a CSV file. We have also an BVH transfer tool. That means after a transfer or a remodeling of the BVH file, because we need to map the joints and so on from the digital human model or the skeleton of AnyBody to our EMA skeleton. We need to map some points and so on. Then we get an output like before, the AnyBody output, like also today, with muscle activities, joint forces, moments, and so on, and TXT text files or Excel files, but also, I've shown it in the video, the motion optimized BVH file that we can re-import in EMA here in the last step, the motion optimized BVH file, and do our further analysis, as I shown in the example, time and assessments like EAWS. And this means how it works in EMA. Maybe a short live demo. My screen should switch now, and what you see here is our EMA Work Designer. our development here the last 15 years, approximately 15 years. It means also we have a 3D view here, full 3D engine developed, and also objects like in a CAD software system. If you already know CAD software systems, it's quite the same in the structure, hierarchical order, parent-children structure and links between. And yeah, you can do here layouting. It's an example from a small plant. And I have also already prepared an example here for the normal EMA. Here is a motion generation based on our work tasks. You see it here. I've mentioned it in the small theoretical part. Pick object, place object, screwing together. Pick object, place object, work. It's a gearbox example, quite easy. Based on parameters, this means I only need to link, okay, which work tasks and which part I want to assemble. And then you get different results like work paths, ergonomics, and so on. But now, when it comes to use the interface, and this means I have done a first simulation, and I have transferred it via the Windows patch in AnyBody, and I created a new motion GmbH file. That means also we can integrate such GmbH files quite and easy. It means, first of all, I want to create a new digital human model. We have a so-called digital human model configurator. Here you can see it in a new window with different nationalities, gender, body height, percentile, age groups. You can also do individual digital human models, but I don't want to go into detail for now regarding also the time. But we create a digital human model, first of all. Here you see it, you can move it around like layouting functions like in every CAD system. And now you give him this work tasks. Oh, one moment, we need to zoom in. Here you go, perfect. And then you create a new work task. It's called mocap data here. And now you import the new GmbH file, the motion data file. That means here we have the GmbH file optimized by AnyBody. And also what we need is the so-called mapping table. That means also the mapping between the skeletal structure of the digital human model of AnyBody and our EMA model. Also, it comes with our software system here, was also part of the research project. And now we have some optional parameters, but I only want to use current position of digital human model. Now I simulate here, press this little button. And now it simulates this worker, but also this worker now here very easy. And now we see the movement of the AnyBody movements from the biomechanical simulation in EMA Work Designer, the tool for 3D production planning. But it's not all, because now you can also play around with these work tasks. That means I can copy it here, very easy, drag and drop, simulate again, and can now connect different work tasks, different movements from AnyBody in EMA together. You can also cut, you can paste, copy these motion capturing files. And here, you see, it does now as the work test 2 times. But also, and that's I think also very quite interesting, you can now connect it together, because maybe you don't have any motion capturing data ready, or you forget some work tasks before the biomechanical simulation, that you can also enrich the simulation now with work tasks from EMA work task library. Like here, very simple example, a work task is to say, okay, between both motion data files, we want to work. Here, it's a small work task I can add into simulation. And I say, okay, I need a new target location. I set here a target. It's like a shadow of the digital human model. And I simulate again. And now I integrated a different other work task automatically generated by EMA, but in connection with the AnyBody movements. And this brings me also to more ergonomic analysis, productivity analysis, like work paths, or also ergonomic analysis here, limit values, German standards, or different other kind of results. We have many results here in the software system, especially also for time analysis and productivity analysis and so on. And this means also I can now connect both worlds of biomechanical simulation with 3D process planning, production planning. And this we have also enriched in the further development. That was the first part to implement an EMA to AnyBody interface, but also we have integrated in the Digital Exonomics Research project exemplary exoskeletons for shoulder and back support. Like here, we have enriched the human model configurator with several kinds of exoskeletons, and also like in AnyBody, we can simulate the exoskeletons in EMA, also with the movements of AnyBody. But also here, it was also an addition in the research project. We can know the consideration of exoskeletons for use in ergonomic assessments. Like here, a little example, small example in the lower right corner for the EAWS. It's a method. They have also a new functionality to do an assessment for exoskeletons, especially for the shoulder exoskeletons here. It's the limit. But then you can also consider exoskeletons in a 3D production planning software tool, and also, of course, in AnyBody. Yeah, this comes to my conclusions here in this small part from EMA to AnyBody. That means we had created a first link between the worlds of biomechanical human modeling with AnyBody and 3D production planning with EMA Work Designer. And this means a prototypical interface between AnyBody and EMA Work Designer, the Windows badge, the automatically simulation of AnyBody in the background, and so we import in EMA Work Designer, which provides enhanced ergonomic evaluations and, of course, also improved visualizations of movement based on biomechanical simulations. And I think, yeah, this is quite new and very interesting, especially also for an outlook. That means also, I think, also in the future, you can use many more functionalities from EMA and AnyBody to enhance more and more ergonomic analysis in the overall world of production planning. It means, for example, also the consideration of balance conditions in EMA, or also the inclusion of more key features from AnyBody in the EMA graphical user interface, or also in AnyBody when it comes to EAWS, NIOSH, muscle activities, joint force, and so on. And I think also one very interesting thing is also the feedback from many from our customers is the consideration of fatigue for the work organization. This means also an answer to the questions, okay, after which duration of work tasks I need to rest, the worker need to rest, they need a break, and how long does the duration of the break must be. It is, I think, also in the future very interesting, interesting things we can maybe develop together also with also different other companies here in the future. Yeah, maybe one last slide. If you are interested in EMA Work Designer, yeah, please feel free to inform you and our website. You can download our demo version for free. We have also free tutorials available in our EMA Academy. And of course, if you are now interested or you want to have more questions also besides the webinar, you can also do the FAQ session after support from Lucas. Feel free to contact me every time. Here are my contact data. I think also we will share it after the webcast webinar here. And yeah, then thank you for watching, and I want to hand over to Lucas.
Good afternoon, everybody. My name is Lucas. I'm from the OTH in Regensburg, and I will now give a short presentation about the Captury AnyBody interface that was also developed as part of the Digital Exonomics project. So just a quick overview in the beginning. I would like to talk about the model itself a little bit, and then I'm going to show the results of 2 studies where we compared joint angles in the first study and joint reaction forces in the second study between a Captury model, so AnyBody simulations with the Captury input, and a Vicon model, so a gold standard marker-based system. For the model itself, the Captury model is basically based on the plug-in gate model from the AMMR that you already know if you are familiar with AnyBody. The difference, or the biggest difference between the Captury model and the plug-in gate model is the so-called virtual marker set. And what this means is that instead of real physical markers that you place on the subject when you do marker-based motion capture, we use the so-called virtual markers. These are created in Captury, so in the Captury software itself. And the way we did it for our model is that we created 3 markers for each segment. So we have 1 marker, which is defined to be in the segment origin. So for example, if you look at thigh or femur as one segment, then the first marker would be in the hip joint. So it would be hip 0 here. Then the second marker is defined at the end point of the segment. So in this case, would be hip E. And then we have a third marker, which is just shifted laterally relative to the marker which is placed in the segment origin. And with these 3 markers, we can now completely define the position of the segment and also the orientation in 3-dimensional space. And since we can export these virtual markers as C3D files from Captury, we now have the possibility to do simulations with AnyBody, because we can now use the C3D interface that we have in AnyBody and that we also use when we do traditional marker-based motion capture. Another difference is that we don't do any parameter identification. So usually when you do marker-based motion capture and then the simulation in AnyBody, you would do a parameter identification first, where you optimize your marker placement and segment dimensions. However, for the Captury model, since these virtual markers are always placed at the same positions, we don't need to optimize marker position any further. And since these markers also define segment dimensions, we don't need to optimize these either. So by placing the markers at the origin and at the end of the segments, we can also calculate segment dimensions from the marker positions for all segments except for the end segments. So for the head, the hands, and the feet, this does not work yet because here we do not have a defined endpoint which would give us the right segment length. Limitations we have noticed so far with this model are, on the one hand, a very high sensitivity regarding the load time position. So when there's a high difference or the position of the model during load time is too far off from the position of the subject in the first frame that you want to simulate, then you get a kinematic error. And also we do see some problems with ankle flexion, where for some simulations the ankle flexion is too high, which then results, of course, in unrealistic muscle activities, joint reaction forces, and so on. So for the first study where we compared kinematics between markerless and marker-based motion capture systems in AnyBody, we recruited 18 subjects to our laboratory and had them perform the following range of motion movements you can see here in these small videos. We recorded motion on one hand with our Vicon system, so marker-based, and on the other hand with the markerless system that is in our case version 250 of Captury. Subsequently, we did simulations in AnyBody. So for both data sets from the marker-based and from the markerless motion capture, we did simulations at 60 Hertz. So the marker-based data was actually downsampled. And then we used C3D files from the physical for the marker-based and from the virtual for the markerless system. And after the simulations in AnyBody, we then compared joint angles using some common metrics like mean absolute error or Pearson correlation, R-squared values, and so on. If we look at the results, we can see here on the left-hand side the mean absolute error for the degrees of freedom in the upper extremity. And we can see that for shoulder flexion, shoulder abduction, and also elbow flexion, we have a quite high agreement between both motion capture systems. However, for elbow supination, we see that we have a very high mean absolute error. So for this degree of freedom, the markerless system really fails to capture the position of the hand or the position of the entire forearm accurately, and therefore we get a huge deviation when we compare it to the marker-based gold standard. And also for hand flexion and abduction, we also see higher errors, and also in case of hand flexion, very high deviations or high confidence intervals. And here we notice that the tracking is not quite stable yet, basically. So we don't have some constant offset or error, but rather what we see is that for some trials, hand flexion works really well, and for other cases, it just doesn't work. So it's not quite fully stable yet. When we look at the head and the thorax, we can see that for the head, the correlation is actually quite high between kinematics from both systems. However, there still is some considerable error or deviation or offset, if you will, between the two systems. We assume that the reason for this is due to the headband the subject is wearing for the marker-based system. So with marker-based motion capture, you have this headband where there are 4 markers placed on it, and then the subject wears the headband, and this way you can track motion of the head. And now if you put on this headband in some little rotated or skewed way maybe, then of course you introduce a constant offset between the actual head position and the headband position. And this is what we see here, where we have some kind of residual error, but at the same time very high correlations. And at the lumbar spine, we can see that some of the motion is actually transferred down to the hip joint. So for example, if you do like forward bending motion to pick up an object, for example, you have this coupled flexion in the lumbar spine and the hip joint at the same time. And what we see here is that when we use the Captury model, the lumbar spine stays quite rigid or stiff, and most of this flexion movement is put into the hip joint, which means that if we compare the overall flexion between the trunk and the lower extremity, then it's actually quite good. But if we look at how this flexion is distributed along all these joints in between, then we can see that this distribution is not quite right for the markerless system, and there is too much motion in the hip joint and too little motion in the lumbar spine. For the lower extremity, we again get quite good results for hip flexion, hip abduction, and knee flexion. So here we see very small errors and also very high correlations. And also, we can see that the root mean square error is actually within the range we see in the literature from other markerless motion capture systems and inertial motion capture systems. However, with ankle flexion, we have this problem that I already mentioned, where sometimes there is too much ankle flexion, so basically the plantar flexion is overestimated, which then of course again causes problems with muscle recruitment and so on. And for the inversion, eversion at the ankle, we have a similar problem as with the lumbar spine and the hip joint, because again we see that some of the motion which happens at the ankle joint is transferred to the hip joint. So instead of inverting or everting the ankle, the model tries to rotate the entire leg around the hip joint. So to conclude the results from the first study, we can see that recording conditions are really improved with the new system because it's just way easier to use when you don't have to place all the markers. However, when we look at results, we see that some of the motion is transferred to other joints. And we can also see that hand tracking definitely needs to be improved. However, at the same time, main joint angles, what we call main joint angles, is for us basically hip flexion, knee flexion, or the lower extremity in general, seems to work quite okay and is as good as other options or other marker-based motion capture systems which are available. However, one more point that we should also mention is that we've only done this evaluation for the AnyBody modeling system. So we compared joint angles within the AnyBody modeling system. Of course, what would also be interesting is to do a comparison of raw joint angles between Captury and, for example, Vicon. Then if we look at the results, or in general, if we look at the second study, the setup was quite similar. So again, we recruited subjects to our laboratory, had them perform some movements. In this case, we recorded a counter movement jump and had them walk at 3 different speeds. Recorded all the movements with both Vicon and Captury. Use the recordings for simulation in AnyBody, where we calculated joint angles, and this time also joint reaction forces and ground reaction forces. And then we did some statistical evaluation to see how the Captury system compares to the gold standard. If we look at the joint angles during the counter movement jump, again, on the left-hand side, we see the mean absolute error comparing both systems. And we can see that the results are quite similar to our previous study where we only looked at joint angles. The mean absolute error is smallest for hip abduction and highest for knee flexion. And we see mostly very high correlation between the joint angles for both systems, except for hip rotation. But here again, might be due to the problem where ankle inversion is actually shifted into hip rotation. And what we have also noticed is that Captury tends to overestimate knee flexion when compared to Vicon. If we look at the joint angles during the walking trials, again, the results are quite similar to the previous study. In this case, the lowest error was during hip abduction for the slow walking. The highest error was found in hip flexion during the fast walking. So what we see is that the faster the walking movement gets, the higher the errors we observe usually. But this time we also have a very high deviation for the hip flexion. So if we just compare the first box plot here between these two movements, so counter movement jump, you see hip flexion ranges to about 10 degrees maybe, And now with walking, we see that suddenly we have a very high deviation in hip flexion. And this is due to Captury overestimating hip flexion during walking movements. And again, Captury overestimates knee flexion, especially for small knee flexion angles. So Captury fails to quite record a fully extended knee. Then if we look at kinetics, so joint reaction force and ground reaction force during the counter movement jump, we can see that the mean absolute error in joint reaction force is lowest for the hip and highest for the knee joint. The relative error between both systems is quite small, so it's only around 3.4% for ground reaction force and 6.4% for the joint reaction force at the ankle. Again, we see very high correlations for all joint reaction forces and ground reaction forces. But what we notice is that Captury tends to underestimate the peak knee joint reaction force in the knee and the ankle joint. So Captury fails to quite get these peak forces right for the counter movement jump. And if we look at the joint reaction forces and ground reaction forces during walking, then again here, lowest error in joint reaction force for the hip. Slow walking again, and the highest error is again observed during fast walking, this time at the ankle joint. So we have a similar picture as with the joint angles, where the faster the walking movement is performed, the higher the error we see. But relative errors are still quite okay. So for the ground reaction force, lowest relative error we see is 2.8%, and the highest relative error we see is at the knee joint during fast walking with 7.3%. And again, correlation is quite high for all forces for all different speed conditions. But again, we have problems with peak joint reaction forces. So in this case, Captury tends to overestimate peak knee joint and ankle joint reaction force. And we can also see that the error range we observe also increases with the walking speed. So to conclude, the kinematics from the second study are basically comparable to our first study and also to literature values. And with most or some of the errors, we are actually within the accuracy range of marker-based systems. So even when you use marker-based motion capture, there's always some uncertainty to your results, so you never get the exact joint angles, obviously. And with some values, we are actually within this accuracy range that we know from marker-based systems. So we can say that overall, kinematic results are quite good, also from the second study. However, as we have seen, we have problems, especially with knee joint reaction force or peak knee joint reaction force, where Captury overestimates knee flexion for small knee angles, and this then results in very high forces in the knee and ankle joint. In general, the relative error we observe is below 8% for all joint reaction forces. However, this is not true for the peak joint reaction forces. So here we really do have differences between Captury and Vicon. But overall, we can say that most of the relative deviation in joint reaction force that we see is again within the accuracy range of musculoskeletal models. So with musculoskeletal simulation, in general, it's of course the same, where you never have an exact result. There is always some residual uncertainty left. And with most of the results we see here, or most of the errors, we are actually within the range of this uncertainty. So to sum it up, what we have achieved here in this project is that we have a motion capture model for AnyBody and Captury with a largely automated data input pipeline. So all the marker placements done in Captury, the segment lengths are calculated in AnyBody, so we can actually minimize user error when you no longer have to place markers or measure anthropometric data. We also can greatly reduce the recording effort with these markerless systems. And as we have seen from our studies, the accuracy of kinematics and kinetics that we get from this system or from our model is actually comparable to values from literature and to other motion capture systems. However, peak joint reaction forces still pose a problem, at least for our model. This already brings me to the end of my presentation. Here at this point, I would like to mention that all of the work I just presented was actually done by my colleague, Dr. Simon Auer. So he was the one who worked on the Digital Exonomics project, and he was the one who created the model and also conducted all the studies that I've just shown you. Simon recently finished his PhD, so he's no longer here with us in the laboratory. And that's why I got to do this talk for him today, but all the credit for the work actually belongs to Simon. And then I think we still have time to take a quick look at the model. So I will just share my AnyBody with you. I hope you can see that. And here I have already opened our AnyBody Captury model. And as you can see, it basically looks just like the plug and gate model, if you're already familiar with that. And the way you would use the model is actually the same. So you have your main file, and if you open and load the main file, you get here the links to the trial-specific data, subject-specific data, lab-specific data, and then to the AnyBody motion capture framework in general, just that you would, not just that you know it from the plug and gate model already. And if we go into trial-specific data, then here we can select the trial file name, so we can specify the name of the input file, the C3D file you want to use for simulation. And then we can also set the frames for which we want to do the simulation. So again, just like in the plug and gate model. And down here, we can adapt the initial position if there is a kinematic error because the load time position of the model is too far off from the actual subject's position. And then if you go back to the main file and into subject-specific data, we can see here it's where you would enter your anthropometric data that you have recorded from the subject, so body mass and body height. And here we no longer have to manually put in all the values. So for segments that are not end segments, so upper arm, lower arm, thigh, shank, and so on, we can actually simply calculate segment dimensions from the C3D file. So instead of putting in values manually, we just reference this calculated value and the model does all this for you. And then finally, in lab-specific data, also very similar to the plug and gate model. The only difference here is that we use our Captury marker protocol. So instead of, for example, plug and gate or any full body marker protocol, you would use this marker protocol here, or of course your own marker protocol if you want to define something else. But in here it's also just like the default marker protocol. So you define your markers, and then down here you just specify on which segment the marker is placed and the relative position of the marker relative to its parent segment. And that's basically how you use the model. So when you do have your own data and want to do simulation, all you need to do is go in trial specific data, set the trial file name, first frame, last frame, and then up here you can just select run analysis and hit execute. And since we don't do parameter identification, you can already start with marker tracking. So basically you just load your CVD file, specify the frames, load your model, and then you click on run. And as we can see here now, it's already doing marker tracking. And then when it's done that, it should be over any second. Yeah, we now do inverse dynamics, and that's basically all you need to do to use the model. Okay, I think that's it from my side. And then I guess if there is still time, we can do some questions.
Thank you very much, Lucas. So could you just mention how people can get access to the model?
Oh yeah, sure. Sorry, I forgot. And so currently our model is not available yet for the public. We do plan to upload it on GitHub. So that should happen anytime soon. But in the meantime, if you are interested in the model, please do contact us, and then we can share the model with you.
Perfect. Thank you very much. I think it's important not to forget that. So if people want to use it, then please get in touch with Lucas. But again, thank you, Lucas. Thank you, Sasha, for 2 interesting presentations. And just before we take a few questions, I would like to say a few words about our online resources. So if you want to know more about AnyBody technology, then you can go and check out our website, anybodytech.com. And here you can find different events, special dates, and also all of our previous webcasts. You can also check out our community website called anyscript.org. And this is really for people using AnyBody. And here you will find multiple online resources, such as our wiki page. There are several blog posts and also links to our repository sites. And it's also here our forum is located, so you can go and ask questions and see what other people has asked in the past and see the answers from us and also other AnyBody users. Then I would like to highlight a few events. So if you happen to be in the Chicago area on November 7th to 17th, then I will be there as well. And if you would like to meet up with me and discuss how AnyBody simulations could add value to your work, then please send me a message and we will set up a meeting. And also, if you happen to attend the annual meeting of the Danish Society of Biomechanics in Roskilde on November 22nd, then stop by our booth there and let's talk a little bit about musculoskeletal modeling. And then I would like to mention that we maintain a publication list of different articles using AnyBody on our websites. And this publication list recently achieved 1100 publications. So you can go there and filter it by industry, research area, or body part to see what other groups have been doing with the software, or just to get an idea of what the software can be used for. And with that, I would like to thank you for your attention so far.